So, a very good afternoon to everyone. Welcome to the fourth lecture on Introduction to Geosynthetic Applications. Till previous class, in yesterday's class, we studied the basic requirements or the basic steps which we have to do in order to design a reinforced soil wall, right? So we saw that in the previous class in yesterday's class. So what we are going to do today is that we are going to solve some design problems. Okay, design problems. So please uh, follow this lecture very carefully and see how all the steps are done. Ultimately, how we are designing a reinforced soil wall. So this designing method is actually very academic. This is not exactly what is that means. The basic steps are same, but we have this problem that I've taken from the designing with geosynthetic book. That problem is quite academic in academic standards. Problems of the academic standards. That means that you will be able to understand how we do the basic designing, but it does not have some intricacies which we generally have to take over, which we have to consider while we actually design a reinforced soil wall in the field. So when we actually design the reinforced soil wall in the field, so their design is actually governed by several codes. Okay, so this is governed by several codes, in the standard codes or British standard codes or uh, your ASTO codes. Okay, so there are various codes which actually govern this designing method. So we won't be following any particular code, but we will be just solving just to understand what is the main mechanics or what is the main concept behind designing of soil wall. So that's why this problem will be just for an academic understanding how we do that. All right, so let us start our class. Let us start the lecture today. And if you have any issues during the lecture, please feel free to interrupt me and ask me, or or these lectures will also be uploaded, right? Uploaded, and you can also view them at any time. So please feel free to contact me over email, WhatsApp, anytime if you have any problem regarding anything. Okay. So I hope that this lecture will be beneficial to you to understand how we do the basic designing of a reinforced soil wall. And since this designing of reinforced soil wall or reinforced soil structure is one of the main key highlights of this course, so I urge all of you to please follow this course follow this lecture, actually this lecture minutely. All right. So thank you again for all of you for attending this course. And so let us begin one by one. Okay. Let me share the screen. All right. I hope the screen is visible to you. Is so the question is the problem statement is quite big. So let us read it very slowly. Let us try to read and understand what is asked in the problem. Design a 6-meter high wrap around type of geotextile wall that is to carry a storage area of equivalent dead load of 10 kPa. It means we are asked to design a 6-meter high reinforced soil wall, and that reinforced soil wall is of what type? That is a wrap around geotextile wall. So if you remember from the yesterday class or from the second lecture actually, where we saw the picture of a wrap around geotextile wall, a wrap around reinforced soil wall, where we discussed the type of retaining walls. There we had discussed this wrap around wall also. So we are asked to design a 6-meter high wraparound type of geotextile wall that is to carry a storage area of equivalent dead load of 10 kPa. So over that wall, over that wraparound geotextile wall, what you have to do, there has to be a storage area has to be constructed. And the storage area has an equivalent dead load of 10 kPa. Okay, so the 10 kPa dead load is coming over that reinforced soil wall. The wall is to be backfilled with a granular soil. SPSP means poorly created sand, right? Having unit weight 18 kilonewton per meter cube, friction angle 36 degree, and cohesion 0. So unit weight is 18 kilonewton per meter cube, and the cohesion is 0, but the friction angle is very high, that is 36 degrees. Okay, so obviously we have to choose the backfill always, which is a very high friction angle. Okay, that is our requirement. A woven silt film geotextile with warp direction, ultimate white with tensile strength, 50 kilonewton per meter. So woven slit film geotextile that I discussed in the first lecture, right? So there are no woven geotextile, there are non-woven geotextile. So this slit film type of geotextile, I told you to see in the book, right? I told you to see there are two types, slit film and one other slit film monofilament, and that other thing woven slit film. So these things I asked you to see, and I hope you all of you have actually gone through that part in that book. Okay, so even silk trim geotextile with warp direction, ultimate way. Warp direction is in the machine direction. So we have a machine where we do this weaving of the geotextile, right? We have the machine. So there are two directions. One is the direction in which the geotextile is being made. Okay, the role of the geotextile is being made. That is the warp direction or the machine direction. And other is the width direction. That is the cross machine direction. So in the warp direction, that is the machine direction, the ultimate wide cubic tensile strength, the ultimate tensile strength of the geotextile is 50 kilonewton per meter, and friction angle with granular soil of 24 degree, means the friction angle between the geotextile and this granular field that we are using, that is 24 degrees. That is the coefficient of friction between the geotextile and that of the granular field that is being used is tan of 25 degrees, right? So is intended to be used in its construction. The orientation of the geotextile is perpendicular to the wall face, and the edges are to be overlapped or sewn to handle the weft direction. Means, so sir, this is the facing of the wall. This is the facing of the wall. And like this, we are placing the geotextile. So in this direction, we are placing the geotextile. So one layer of geotextile, then two layer of geotextile, then three layer of geotextile, like this. This is the facing direction, face of the wall. This is the face of the wall. And like this, one, two, three, like this, we are putting the geotextile perpendicular to the face. In the other direction, that is in the out of plane direction, in this direction, okay, in this direction, out of plane direction, obviously the width of the one geotextile is limited, so what you could, two geotextiles have to be overlapped. Geotextiles have to be overlapped together. So it has to be overlapped and sewn. It has to be sewn with a machine. We have to sew it. Okay, in the other direction, this is the cross machine direction. So it is placed in this machine direction, this longer side machine direction. The other side is my cross machine direction, perpendicular to this screen of this screen. So that is a cross machine direction. A factor of safety of 1.4 is to be used along with appropriate geotextile reduction factors. Okay. So let us start. So initially, if you remember from yesterday's session, from yesterday's class, so what is the first step that is? The first step that we have to do is that we have to ensure the internal stability. Also, you have to ensure the external stability. So both the internal and the external stability of our system has to be ensured. Right, both the internal and the external stability of our system has to be ensured. Okay. So let us see. So what will be our first step? Our first step is to determine the horizontal pressure at any depth. Okay. So let me write it here. First step is horizontal pressure is a function of depth Z. Okay. So determine the horizontal pressure as a function of depth z. Okay. What we want to do? This means we want to why do calculate the vertical spacing of the reinforcement, which is SP. So determine the horizontal pressure as a function of depth z. So due to it, what we are doing, we want to calculate the vertical spacing of the reinforcement SV. So vertical spacing we want to determine. So first you have to calculate the horizontal pressure as a function of depth. So when you determine the horizontal pressure as a function of depth, what we will be getting, we will also from there we can also get the force that is coming, load that is coming on at each level on the reinforcement. Okay, the load that will come on each level at the reinforcement. So what is my Ka? Ka is the active earth pressure coefficient. Okay. So what is my horizontal pressure? Horizontal pressure is my horizontal pressure that is coming from the active earth pressure and horizontal pressure that is coming from the that is horizontal earth pressure that is coming from the backfill and horizontal pressure that is coming from my surcharge. Right, horizontal pressure that is coming from my backfill and horizontal pressure that is coming from the surcharge. Okay, so like this it is there, right? So also about your surcharge. So due to the soil also you have some horizontal pressure and due to the surcharge Q is also have a horizontal pressure, right? So that you are done. This is nothing but K times gamma into Z. Gamma is the unit weight of the soil. This is directly just K into Q. So what will be this? 0.26 times 18 into Z plus 0.26 times Q. What is my Q? I will directly write this. Is 10. Okay, so this is my basic equation. Now what is the thing? Now we are given the ultimate tensile strength, right? This is my horizontal pressure exciting. Now, what is my ultimate tensile strength of the one geosynthetic? It is given to you now that ultimate value we have to bring it to the allowable value, right? By dividing by certain reduction factors. If we remember from yesterday's class, so we have to divide the ultimate value by some reduction factors to get the what? To get the what? To get the allowable value, right? To get the allowable value. That we will do. T allow is T ultimate by reduction factor installation damage, reduction factor creep, reduction factor chemical, biological damage. So ultimate is 50. And for the reduction factors, we will take some standard values 1.2, 2.5, 7, 50 divided by 3.81. Right, so this will come out as 13.2. Okay, now to ensure that we have there are two parts in our internal stability analysis. One is the rupture criteria, another is the pull-out criteria. To prevent rupture, if you remember, if you recall from yesterday's class, you will remember that to prevent rupture, we need to ensure that the load that is coming onto each of the reinforcement at any depth, the load coming on that reinforcement or the geotextile in this case has to be less than the allowable strength, allowable tensile strength that you have to ensure to prevent rupture, isn't it? So load coming on each reinforcement, these should be less than the T allowed. Why? To prevent rupture, right? To prevent rupture. Okay. Now, what is the load coming onto each level is nothing but the spacing as V times the horizontal pressure. So if in yesterday's class you might have remembered that what is the load coming? We had written it as K coefficient times the vertical pressure sigma V, K times sigma V times SV. Now K times sigma V is nothing but the horizontal pressure that we have already determined. So SV time spacings time the horizontal pressure, that is the load coming on each reinforcement. So that SV times this horizontal pressure should be less than the allowable tensile strength of the reinforcement. So for that we write what? T allowable by we use some factor of safety. Okay, since it should be less than T allowable, that's why divided by some factor of safety. Okay, so what will be my spacing? So is right. So this factor of safety 1.4, it is already given to us in the question. Okay. Factor of safety of 1.4. So we have used 1.4. So sigma h, we put this equation, this 0.26 into 18 into z plus 0.26 into 10, that is nothing but this 4.68 z plus 2.60 into 1. So from here, what we get a relation of the speed with the as a function of z, that is the depth. So get the spacing as a function of depth. So you will see that as the depth is higher, the spacing will be lower. It is denser configuration. You have to place the geotextile in a dense configuration. But as the depth will reduce, as the depth reduces, the spacing also increases. That means scarcer density of the density of placement of the geotextiles. Right, so you got SV, that is a spacing as a function of depth z. So now that means the selecting the appropriate spacing actually satisfy our one of our internal stability criteria, that is the rupture criteria. So selection of appropriate spacing satisfies the rupture criteria, rupture prevention criteria. Okay. Now we will do some trial and error to determine the spacing. So our wall is 6 meters. So first let us see for z equal to 6 meter, how much spacing we are getting. We'll get if we put z equal, find out if we put z equal to 6 in this above equation, see how much you are getting. See how much you are getting. 13.2 divided by 4.68 into 6 plus 2.60 into 1.4. We will get this will come as 0.307 meters. So this much spacing should be there at a depth of 6 meters. So let us use 0.30 meter. Okay, lesser than that we will use. Okay, now we will do some more trial and error. Okay, for some more trials we will do. Okay, for z equal to 3.3 meter, let's say. What will be my SV? See how much is it coming? See how much is coming? Just give me a second. Yeah, so sorry for the interruption. So this one comes out, this will come out as 0.52 meters. Okay, this will come out as 0.52 meters. So 0.52 meters means we can take around 0.5 you can take, right? So 0.5 you can take. So 0.52 means we can take around 0.5. So let us use script. And again, let us see on some lesser height. So 1.3 meters. This V is 13.2. Meters. So we can use. Let us take 0.65 meters. So why we'll see. Let us use 0.6. Why I am taking 0.65 meters? Because see. So initial, what we are doing. So initial at 6 meter, we are using 0.3 meter at 6 meter depth, 0.3 meter spacing we are using. And at 3.3 meter, we are getting 0.5 meter. Now my total height is 6 meters. Right, total height is 6 meters. At from bottom here, so this is 0, right? So this is 0 level, this is 6 meter level. Now at 3.3 meter means at here at 3.3 meter, at 3.3 meter, at 3.3 meter, at we have a requirement of from means above 3.3 meter, we can use 0.5. But below that, we are using what? We are using 0.3 meter for. So what let us do? Let us use 0.3 meter in this region. Okay, 0.3 meter in this region. So 0.3 meter means how many how many layers of geotextile will come? How many layers of geotextile will come? So 6. So 6, 6 minus 3.3. So this height is 2.7 divided by 0.3. This way there is 9 layers of geotextile will come here. Okay, 9 layers. Now above that we are using what? 0.5. So up to 3 point from 3.3 to 1.3. Okay, this is 1.3. 1.3, let us use a spacing of 0.5 meter. 0.5 meter. That means what? That means what? 3.3 minus 1.3 divided by 0.5 will come out as 4. So 4 number of your textile layers let us use here. And for the remaining 2, we'll be using 0.65 meters. So 2 numbers. So that's why I have taken 0.65. My requirement is of 1.08, but I'm using lesser than that 0.65. So that is it will be fine. So this is how we are to arrange our geosynthetic. So this depends upon the designer. It depends upon you to decide. Now instead of 0.3 meter, you can even take. If you want to be more safer, you can take 0.2 meters also. It depends upon the designer, but it should be less than my this one. So it depends. Okay, it is up to you to decide. It is up to you to decide what spacing to take, how to arrange such stuff. But you have to ensure that the spacing should be less than the SB that you are calculating. Okay, so this is my requirement. So now if I want to draw that diagram, so how will it be? Let's see. So total there are how many layers? So first we have, there are how many layers? 9, 12, 15 layers, right? 15 layers total. So we have one layer. Okay. Then we have 2 layer. We have 3 layer, 4 layer, 5 layer, 6 layer, 7 layer, 8 layer, 9 layers. So these 9 layers,
this 9 layers. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 9, we are putting at 9 layers at 300 mm spacing, means 0.3 meter spacing. This we are putting. Then we have 4 layers at 5.5 meters, 500 mm spacing. So increase the spacing. Yeah? 1, 2, 3, 10, 11, 12. So 1, 2, 3, 4. Okay, so this is 4 layers at 500 mm spacing. And then we have the remaining 2 layers. Okay, this is the top. So remaining 14, 15. So this is the last layer. This is the top. This is my top. This thick part is my top. So 15, it means we have 2 layers at 1, 2, 3. Oops. This is 2 layers. Okay, so total I have 15 layers, right? So 1 layer, 2 layer, 3 layer, 4 layer, 5 layer, 6 layer, 7 layer, 8 layer, 9 layer at 300 mm. Then 1 layer, 2 layer, 3 layer, 4 layer at 500 mm. Then 1 layer, 2 layer at 650 mm. So this is my spacing arrangement. Okay, this is my spacing arrangement. Now the next step is to determine the length of the reinforcement layer, the length of the layers. Okay, length of the layers. So now if you recall, for flexible reinforcement, I'll take it later. For flexible reinforcement, we have this active wedge as the rupture plane. We take this active wedge as the rupture plane, 45 plus 5 by 2. Right, 45 plus 5 by 2, we take as the rupture plane. Now, what will be my length of reinforcement? The length, so we know this height, total height I know. Okay, now at any depth Z, say, if I want to find out, the length of the reinforcement, that is LR plus I have to do my embedment length. So my total length of the reinforcement is LR plus my embedment length, LR plus my embedment length. So LR I can easily find from the geometry of the diagram, because I know the angle, like from the geometry I can find it out, LR. For LE, I have to calculate the embedment length, and that calculation we already discussed in the previous class. In your studies class, we already discussed, if you recall, right? How to find out this embedment length, isn't it? If you remember, so LR you can get from my geometry. So this, how much is my length? This I can get from my geometry. And rest, the embedment length I have to get from my what? Get from my calculation. So this green is my total green part is my reinforcement. It has two components, LR and LE. Okay. LR and LE. Now, how to get the LE? So how to get the LE? So LE will be equal to, write it properly. First part was, second part is to determine the length of the reinforcement layers. Okay, so my LE is, I can write as V times sigma H times a factor of safety. Right, so SV times sigma H is what? Is the amount of load that is coming on each reinforcement layer. So that we are multiplying by some factor of safety just to make it safer, conservative design. So we are multiplying it by some factor of safety, the load that is coming on each layer. Then delta. Now is V times 0.68 Z plus 2.60. This is my horizontal pressure. We already determined it beforehand. Into factor of safety, I think 1.4 again plus 2 C. So this term 2C plus sigma Z 10 phi times LE. So it is nothing but the frictional resistance that is developing here. Okay, the two, because upper layer, upper surface and bottom surface, two surfaces are in contact with soil. So we have 2 times LE. LE is this length of the interval times C plus gamma Z times tan delta. This is nothing but what? The shear resistance, the shear resistance that develop at each of the surface. Okay, the shear resistance is nothing but the shear resistance. C plus sig gamma Z tan delta, gamma Z tan delta. Okay, this is nothing but the shear resistance. C is the cohesion, gamma Z is the vertical pressure at any object, and tan delta is nothing but the friction coefficient. Right, so that will give my shear resistance that develops between the soil and the reinforcement. So C is 0. Is given as 24 degrees, delta already given with us in the question. So I will get SVS 6.55 Z plus 3.64 divided by 16.0 Z. Okay, let's check this once. Just give me a second. Just punch the numbers in the calculator once and just recheck. 2, divided by 2 into 18 times 10, 24. Comes out to 16.02 it. So we are taking around 16. Okay, 16 just to be conservative. So it's fine. 16 is fine. Then 4.68, 0.4, then 5, 6, 0.4. Sorry, 2.6 into 1. 3.6. It's fine, huh? It's fine. So we get this LE also as a function of Z and spacing. Okay, we get LE as a function of both the depth Z and also as a function of spacing. Now what we need to do in the next step, we need to make a chart or a table. We need to construct a table. So in the table, my first column will be layer number. Okay. My second column will be depth is Z in meters. Then I will add my spacing also in meters. Then I have my LE that I will find out, that is meters. Then I will have my LE minimum. Minimum LE that has to be given. Okay, that will be my LE minimum. But my LR, the LR that I will calculate, it is my LR that I have to write. Now the total L calculated means LR plus LE. That will give my total L calculated. That will be also a meter. And finally, I will give the L specified that I am actually going to use in the design. That will be my L specified. Okay. Now LR. So LR. So L you get like this, and LR, as I said, you directly get from the geometry. LR directly you get from the geometry. How? H minus Z, then 45 minus 5 by 2, minus 5 by 2, 5 is 36, 6 by 2, but 6.0 minus Z into 0.509. So this is my LR. Okay, I also got my LR. So LR is also a function of Z. L is a function of both Z and SV. Okay, so this I got. Okay, so there are 15 layers. So I will try to make 15 like 1, 2, 6, 7, 8. Should have shorter. So 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So total 15 layers. So all the layer numbers I wrote. Now depth is what? First layer 0.65 meter, right? Then 1.3 means 0.65 plus 0.65, 1.3, then 1.8. Because see my this here depth is 0.65, 0.65. Then next my depth becomes zero point 0.5, right? For 4 layers. This will be 2.30, 2.80, 2.30. Okay, then everything is 0.30. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 layers, 0.30. 3.60, 3.90, 0.20, 4.50, 4.80, 0.10, 5.40, 5.70, 6.00. So we got all this right. Now we have LE, LE. So what we do, so it's better that we make a Excel sheet for that. Okay, make an Excel sheet. So I will just will share the screen.
Okay, I hope that the screen is visible to you. So what we will do, we will make the similar sheet. Let us make it in Excel. Okay, then it will be easier for us to do everything. This layer, layer number. Then we have Z in meters. Then we have SV in meters. Then we have LE in meters. Then we have LE minimum in meters. Then we have L R in meters. Then we have L calculated in meters. Then we have L specified in meters. Okay, so this is our chart. I will just edit it. Just a second. Just do everything properly. Okay. The layer number 15 to what 15, 14 like this up to layer number 1. I have to go now. Layer number 1. And what is my depth? First depth is 0.65, then 1.30, then 1.80. One more thing. Then this is plus 0.5. And 3 four layers. So this is 0.65. 0.65. I have 2 layers. The rest is 0.50. Right, 0.50. 0.5 layers. 4 layers. And rest is my 0.30 space. Full here is plus 0.0. Done, right? So I got my all the Z correctly, SV correctly. Now, what was my LE? What was my LE? Let me see. LE is equal to SV times 6.55 Z. 6.55 times Z plus 3.64. Right, right. Divided by 16 into Right. Okay. So my LEs, I got my LEs. So just take it and pull it down. So yeah, so my LEs are coming this. But the what is my minimum LE that I have to give? The minimum LE, the minimum LE that I have to give is nothing but what? The minimum LE that I have to give is 1 meter, right? 1 meter I have to specify. So one. My in LE minimum is one. So everything is less than 1 meter, right? So everything is. So let me make one more. I will let LE. Let me put this LE used. And this is LE. Hmm. Okay, so my LE used will be what? 1 meter itself. Okay, will be 1 meter itself because that is my minimum LE because all the LE that are all the LEs that are calculated that are less than 1 meter. So I have to use 1 meter. Now what is my LR? LR was 6 minus Z times 0.509. Right. This was my LR. So calculate the LR like this. Okay, so what will be is my LE calculated? LE calculated is nothing but LR plus LE used. LR plus LE used. This will be my calculation. Okay, so these are the calculated lengths of the various layers of reinforcement that I'm using. Okay, these are the calculated length of the various layers of reinforcement that I am using. Of all the 15 layers, these are my calculated lengths. Now, what to specify? How to specify? So see, from here to here, what I can do, I can take use 2 meter, right? So we merge it 2 meter. I can use right 2 meter. I can use so minimum this much L I have to use, but I'm using 2 meter. Now from here to here, what I can do, I can use 3 meters. 3 meters I can use. It depends upon you. Okay, it's completely in your hand what to do, what to do, and from here to here I can take 4 meters. It's completely up to you. It's your decision. It's the designer's choice. What value to select. Okay, what value to uh, it's completely the designer's choice how to specify the length. But you have to ensure that this length is always greater than this calculated length. Okay, this length should be always greater than this length. Okay, all these lengths I can see this 3 meter is always greater than all this length. 4 meter is always greater than all these lengths. 2 meter is always greater than all these lengths. Okay, so this is how we finish the finish this part of the design. Okay, so what I will do, I will copy it. Ah, I will just put this table in the slide. Just a second, I will show you. So this is the table that we calculated. Okay. All right. Now this step is actually, now what is completed is in all the internal stability steps we have done. Okay, in all the internal stability steps we have already done. Now, what about the external stability? That also you have to do. So when we select the appropriate spacing SP, we satisfy one of the internal stability criteria, it is the rupture criteria. And when we select this length property, we satisfy the pull-out criteria. Now the next step is to also to confirm that the external stability of the structure is appropriate. External stability of the structure. If the external stability is not appropriate, you have to redesign. Okay, so you have to ensure that the external stability of the structure is. Now, just before we go to the external stability, one more thing also you have to ensure that the overlap length of the geosynthetic, that geotextile that we are putting along the out of plane direction, that is the direction perpendicular to the your screen. This out of plane direction, whatever overlap we are putting, that overlap length should be appropriate. Okay, that also you have to ensure. Now that also you have to write to, so you have to write check for overlap length. Overlap length, you must say this is the wall face. Is the wall face, and you are placing say one geotextile like this. Okay, then there will be one more geotextile that you have to overlap. So this is the machine direction. Okay, this is the this is my machine direction. So there is no problem. But this side, the other direction, there is a width constraint, right? So I have to overlap. Okay, I have to overlap this. Overlap. Okay, I have to overlap. And this is my wall. Okay, this is my wall. This is my wall face. So I have to overlap. So now this overlap, this is my wall. Okay, this is my reinforcement one. This is my reinforcement two. Now this this is my overlap length. So this length is nothing but my overlap LO. So this I have to find out. This LO I have to find out. Okay. Okay. So what is LO? So now you are seeing, instead of using two, you are using four because you have four surfaces. So you have four surfaces in contact. So like this one is synthetic is contact like this one. So one, two, three, four. Like this, four surfaces are in contact. So I'm using four. Okay. So you have one geotextile like this, other geotextile like this. So one, two, three, four. Like this, like this. So this is my contact. So one, two, three, four. Four surfaces. So we are using four. Okay. Then CA is what? CA is the addition between the two. Okay, between these two, the addition. This is my CA.
Now again you are seeing this L naught is a function of SV, the spacing as well as the depth. Okay. So now think how we can do this, how to do this. Just think for a minute. Okay. Just think. I hope this four term is clear. Nah? Again and again I'm saying. So these are two, one, two, three, four. That's why. Okay. This surface, this surface, this surface, this surface. So at the contact, there are four surfaces. That's why you're using four. Okay. Now see for this one also what we can do for z equal to 0.65 meter. What is my SV? My SV is 0.65 meter. Right, this is my first layer. For first layer. So my L naught will come out as, so we are seeing my SV is directly proportional to L naught. Means higher the SV, higher the L naught. Obviously, as we go down, as we go deep, means as the depth is more, obviously there is a lot of pressure. So there are less chances of for the geosynthetic to separate at the one length. But at higher up the wall where there is low pressure acting on this reinforcement, low vertical pressure is acting on the reinforcement, there are more chances that this overlap might separate. So that upper portion is more critical to us. So for that we are calculating. So my L naught will, for that my L naught will come out as 0.25 meter. So what you can do, you can use a minimum of 1 meter throughout. It's 1 meter overlap throughout the height. All the layers. 1 meter L naught you can use. Okay. Now the next part that we are going to do, that is my internal stability analysis. Okay, that will be my internal stability analysis. Okay, that will be internal stability analysis. So let us do. So now we will see that while we do this, we are not we are while we are doing this problem, we are not considering the seismic forces and all those stuff. Okay, that because this is we have just kept its way academic level. So but actually when you are doing the design, if it is highly seismic area where you have to construct our this head for soil wall, at that time you have to appropriately consider the seismic forces or not. Okay, so and you already know how to consider them. We already discussed in the yesterday's class. Okay, you already know that. So the main important thing here is that the basic step should be clear to you. The basic concept should be clear to you. Rest everything else you can do. You can complicate it yourself. Okay. So what I suggest to you, what my suggestion will be to you is that you resolve these problems again by yourself, considering seismic forces also. Okay. Consider that you have to design it at a seismic zone 4 or seismic zone 5, say, and then on the basis of that you redo this designing process by considering the seismic forces. Okay, so what I will do, I will just draw whatever we have designed till now. I will draw that part. Okay, first say this is the top, then I have my first layer, and second. Okay, so this is my first layer, this is my second layer. Huh. Arey, the hell is wrong, man? Okay, this is layer 15, and this is layer 14. Okay, from here to here, how much is it? 0.65, right? So 1.8 meters, 0.65 plus 165, 1.8 meters. Then I have four layers. And what is the length of this first layer? See, 4 meters, right? Just take just a second. So then what does the second spacing? 0.5 meters. You're set. How much? 3 to 1.2. 4 layers set how much spacing? 5.5, right? We'll do it. Just complete it first. Yeah, what is wrong with this man? One, two, three. Let's do this. Let me verify it. Huh?
1.8. Just give me a second, na. I will just confirm and do it properly. Just give me a second. Yeah, yeah, it's fine only. It's fine. Whatever we have drawn is fine. Na? Yeah, this is fine. So this is 1.8. Uh, from here to here it's 2.1 meter. So 1.8 and 25. Two, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 into 3. Uh, this is 1.8. 13th layer. 6 solid. 3. Ah, that's why. Wait. I will tell you what the confusion is. Wait. See, the first layer is also at a depth of 0.65. The second layer is also at a depth of 0.65. It's 14th, 15th and 14th.
It's 15th layer, 14th layer, na? 15th layer, 14th layer. So over wrong with this. See, don't know what's wrong with why is it so buggy. So from the top, so above this also you are putting some soil, okay? Yeah. So from here to here, it's 1.8 meters. Hence 165 plus 165 0.5. Here, into 10 meter, 0.1 meter, from here to here it is total here 6 meters. This is the toe. Now, this is how much? This is this width is 2 meters. Okay, then the next that you are seeing here, here, this width is 3 meters, and the longest ones. Okay, the longest one 4 meters. All right. Backfill soil properties are given to you. Backfill soil gamma is equal to 18 kilonewton per meter cube. Delta equal to 5 is equal to 34 degrees. C is 0. And for the foundation soil, that means the soil is there below. For foundation soil, foundation soil, um, 0.955. This one you can take approximately 10.2 degrees. Square CA is also given. Let's see, 16. So we'll see where we need all this thing. Huh? Let's check in the frequency. Just now just match with the table once. So first layer is 2 meter width. This is 2 meters. Second layer is this is 2 meter, 2 meter, 2 meter, 2 meter. Fifth layer is 2 meter. Sixth layer is 2 meter. Seventh layer is 2 meters. 2 meters, 2 meters, 2 meters. Fifth layer is 3 meters. Eighth, ninth, 10th, 11th, 12th. Okay, 8, 9, 10, 11, 12. 13, 15.
See, what my doubt that is arising here is that whatever the solution is given in distribution is done, I cannot match it. Okay, that's the thing. I will show you how the thing is given. In 9 layers, they have taken 2 meter. Yeah. So see, in the book, what they have done, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 layers, they have taken 2 meter width. But when they have made the table, they made it like us itself. So what I will do here, that's why you are getting a little bit confused. What I will do here, I will give the image in, let me insert the image here from the book itself. And when you redo this part, redo this part, okay, redo this part by yourself once. And when you redo, sorry, yeah. So when you redo, what you do, you take the dimensions that were taken from, that were adopted by us. Okay, in that way, it will be much better. Okay, I will write it here. Redo this part as per as per our specs, as per our specifications. Okay, okay. Let us now solve as per what they have taken in the book. Okay, so let us do that. Before that, let me just put the diagram for you from the book. Huh? From the book, let me just put the diagram. Series 20. Let's see.
16. Let me in this part. Let me just insert the diagram from the book. Huh? Just give me a second. Huh? I'll copy and insert the diagram from the book. Let me put it. Wait. How to put it? Put it. Just give me 1 second. Okay, so this is the so this is the this is the like designing that they've used in the this is you can see it is not exactly same to what we have chosen. Okay, so what you will do, you do this part by yourself. Okay, just write again. Obtain for the sake of explanation, I will put the figure from the book for now. Okay, for now, let me just follow this figure, right? And backfill, the properties are given here, backfill 12 conditions. So now let us do. Now, the main step that we have to do is what? We need to do the external stability analysis. So let us do that, right? We want to do the external stability analysis. So first we found the Ka. That's why means I was getting confused that why this diagram is taken. We selected something else, but when I was seeing the checking the solution, there this diagram was there. So I was a bit confused. So whatever be it, so let us for now
do it like that only. Just follow the diagram, whatever they have taken in the textbook, and solve the rest of the problem. But when you do it yourself, you please do by yourself. You take the specifications that were taken by us in the table. Okay. Now, what is the PA that is acting? Active earth pressure. Newton per meter. Now, PA cos 34. Because CPA is inclined angle delta, right? Because we are not considering the wall is smooth. There is some friction. So P is inclined angle delta. PA sine 34 is, that is PA cos 34 is the horizontal component, PA sine 34 is the vertical component. Okay, if you see the figure, you will get to understand. You see the solution in this that book also, okay, designing with geosynthetics, that is done there. You please follow that once. Now, factor of safety overturning. Let us calculate first. Let's calculate the factor of safety overturning. So what you have to do, you have to take all the overturning moments and the resisting moments. Okay. So it will be W1 x1 plus W2 x2 plus W3 x3 plus PA sine delta into 4. So this will be acting at from here to here. Here is 4 meter. That's why we're taking 4. And about the toe, we are calculating. Okay, the moments. So what are W1, W2, W3 that we will see now? Just give me 1 second. We'll discuss that. So time to two. Okay, now what is W1? W1 means this mass. Mass of this block. Mass of this block is W1. Okay, what is W2? W2 is mass of this block. Okay, and what is W3? W3 is mass of this block. Okay, so this is W1, this is W2, this is W3. Okay, understood? So I will erase this, but after that, okay, let me just do it, then I will erase. Okay, let me just do it first. So 6 times 2 into 18 into 1 plus 3.9 times 1 into 18 into 2.5 plus 1.8 times 1 into 18 into 3.5 plus 50.7 into 4 divided by 75.2 into 2. So why 6 into 2 into 18? So 6 is the height and 2 is this. 6 is this height and 2 is the width. 6 into 2 into 18 will give the weight. The next will be what? 3 minus 2, 1 is the width. And what is the height? Height is 1.8 plus 2.1. That is 3.9. So 3.9 times 1 times 18 will give you the weight. And for the last one, again, 1 is the width. And what is the height? The height is 1.8. So 1.8 into 1 into 18 will give you the weight. So that is what it is. Okay. So finally, I will erase it.
Okay, and the lever arms you understand, right? So lever arms at this point, so this weight will be acting at the center here. So 2 by 2, that is 1. It will be acting at the center here. So 1 by 2.5, and this is 2 plus zero point 0.5 from here to here, that distance. Okay, it is 2 plus zero point 0.5. It will be how much? 2.5. So we will see here we have 2.5. Here we have 1. And the next again we have 3 plus zero point 0.5. That's why we have 3.5. Okay, 3.5 is the lever arm. So this is very easy, basic. Clear this so that you can understand it later. Okay. For F overturning is equal to 4.7, which is greater than 2.0, is acceptable. Now next is factor of safety against sliding. For sliding at the base you will do almost the same thing. CA into L plus W1 plus W2 plus W3 plus PA sine delta, all the loads that is coming divided by L times tan of the friction angle. Okay, vertical load times the friction angle is total times L by PA cos delta. Okay, CA is the addition between the geosynthetic and the foundation. So I'll 16 into 2 plus 216 plus 70.2. This times 2 because we are only considering only this part. This part is in contact with the condition. Okay, that is 2.1 greater than 51.5. Okay. Okay, so next, so overturning check is done, sliding check is done. Next, bearing capacity check. So bearing capacity, P ultimate. I will just roughly, very crudely, I'm finding it out. You follow the IS code and find out everything properly. We already solved some bearing capacity problems in the previous yesterday's class. Okay, so it should not be easy. Yeah, it should not be difficult for you. For now, I'm just solving it in a very fast, crude way. That is the P acting. It is 18 into 6 plus 1. This is the total vertical pressure that is there. Total vertical pressure. The vector of safety is 269 by 118, 2.3, 2, which is okay. But here you are seeing directly you are taking this vertical pressure you are taking. But we already know that this one also we have to do. Okay, this thing we have to do. So do this. Okay. This if you want to do as per whatever the proper standards, then this vertical load divided by weight minus 2. I see this one, this thing you can do. Yesterday you already discussed this, that also you can do. But now just for the sake of understanding, easy understanding, you have to. Okay, so this is this problem. So the main point here is that up to this much you have solved, everything is fine. So this designing also everything is fine. But what I suggest is that for this part, okay, this figure directly I have taken from the book, and according to this figure only I have done this second part, this external stability analysis. But what you do, you actually see whether this figure is correct or not. You match this figure with your table to see if this figure is correct or not, and if not, you can draw the figure correctly and you solve it by yourself. Okay, solve it by yourself. In that way, it will be a good practice for you also. Okay, that's why you're doing written the redo this part by yourself, adopting the specifications that were studied by us. Refer to the table. For the sake of explanation, I will follow the figure from the book for now. Okay. I know handwriting is bad because it's difficult to write in this presentation, so that's why you just please manage. Okay. So you do this part by yourself, adopting the specifications that were selected by us. Refer to the table. For the sake of explanation, I will follow the figure from the book for now. Okay, understood? Okay, so let's just see go through this problem for in 2 minutes just once. From one, then we will go to the next problem, last problem. Okay, so this is one more problem. A typical section of a retaining wall with backfill reinforced with metal strips. So now we are using metal strips for reinforcement. Okay, we are using metal strips for reinforcement. Okay. Showed in the figure, so following data are available. Height is 9 meter. B is the width of the width of the steel strips. Okay, steel reinforcement that is 100 mm. Then we have the what? Thickness of the steel strip is 5 mm. F5, that is the yield strength of the steel strip. Steel is 240 MPa. The factor of safety for steel is 1.67. Factor of safety on soil friction is 1.5. Friction angle of soil is 36 degree. Unit weight is 17.5 kilonewton per meter cube. 25 degrees. SV into SH is 1.1 meter. SV is the vertical spacing. So here we are spacing strips, right? We are spacing small strips. So here there is vertical spacing also matters, and the horizontal spacing, like out of in the direction perpendicular, the out of plane spacing is also important. Out of plane spacing as well as the vertical spacing, as vertical spacing as well as the out of plane spacing. Both are important. Out of plane spacing, that is the horizontal spacing, as well as the vertical spacing. Both are important. Okay, so here we are asked uh, required LE and L and LE at varying depths, the largest tension in the strip, the allowable tension in the strip, and check for external stability. So let us do. So gamma H is the horizontal load coming at each level is this. Now load uh, on reinforcement T is gamma H into SV times SH. Right, SV times SH is the load on the reinforcement that is coming. Gamma H, sigma H times SV into SH. Now T is 17.5 times Z times 1 minus sine 36 times SV into SH is 1 by 1 to 1 into 1. So will come out as 4.55 Z. So part strip. Okay. Now LE, what will be my LE? Will be factor of safety times T. T is what? T is the load coming on each strip that I'm multiplying by a factor of safety divided by twice gamma Z beta delta. So it's Z get cancelled up. So LE comes out as 4.14 meter. So this one is my LE, the embedment length that comes. Okay, 4.15 meter. Now see here all the number of steel strips, everything is given in the figure. Okay, there is 9 layers of reinforcement and all those things. Now, if we sum the load that is coming on all the steel strip, it will give us the total load in the steel strips. Okay, so that we are going to do. So previously it was a design problem, the first problem that we, this is not a design problem. The design, everything is given to you, are just to find. Okay. Now summation T is 0.5 plus 1.5. This is the depths. Okay, depth. So see, the first one is placed at zero point 0.5, second one is placed at this 1 meter. Or all the spacings are 1 meter. So the first one is placed at zero point 0.5 depth, the rest all are placed at 1 meter depth, right? Vertical. So that depths we are just taking. Okay. Then we have 2.5, then 3.5, then 4.5, then 5.5, then 6.5, then 7.5, then 8.5. So these are the total Z's. The total Z. This Z. This Z. So 4.55 times this total Z, if I do, that will give me the total load that is coming on all the total load that is coming, right? It will give me the total load that is coming. Just back calculation you are doing. This will give me the total load that is coming. Okay. This is what? This is summation Z. Right? This will be 40.5 into 4.55, 184.27. Okay, now what is my PA? So what this is what? This is the total load that is coming on the all the reinforcements together. All the reinforcements together are taking this much amount of load, right? All the reinforcements together are taking this much amount of load, 184.27 kilonewton per meter. This much load is taken by all the reinforcements together. Now let us see how much load is actually coming. It is nothing but the active earth pressure half into 0.7 it will come out as 184.28 kilonewton per meter. Now you can see, so this load is actually balanced, right? It is nothing but equal to summation T. So my total load is balanced. So total earth pressure that is coming, that is actually taken care of. It is actually balanced by this all the that is the all the load, right? Now is what? Right? So this is at the bottommost depth. Okay, 8.5 meter depth. Okay, this much is my tensile. This much is the load that is coming. Okay, at the bottommost reinforcement, this much is the load that is coming. It is 38.68 kilonewton per strip. Means at that strip, at the bottommost strip, this much kilonewton of load is taken by the bottommost strip. Now T11 with so the bottommost strip will be obviously taking the maximum load because it is the maximum, it is at the maximum depth. So whole load is acting over it. Whole pressure, the complete pressure is taken acting over it. So that's why the maximum tensile load that is coming on the bottommost strip. So this much 38.68 kilonewton is the maximum load in the strip with that is taken and which strip takes this maximum load, the bottommost strip. Okay, 38.68 kilonewton is the maximum load taken by the strip, is one single strip, and that single strip is which one? The strip that is at the bottommost layer. Okay, now what is my T allowable tensile strength is Fa into T into P. Now Fa is Fy by some factor. Okay, 40 MPa given. So in kilonewton, I'll divide by 3. Now, then multiplying by the cross-sectional area, it will come out as 72 kilonewton. Now 72 kilonewton is the allowable tensile strength of the one strip. So this is greater than 38.68 kilonewton. So it is okay. Okay. Now let us come to the length part. What is the length? Is it is LR plus AE. LR is H minus Z, 10. And 4. So we are considering that that is flexible. The steel strips are flexible, not rigid. Considering flexibility, we are designing. Now that's why you are taking 10, this 10 active wedge. H is what? 9 meters. Okay. And LE is fixed as 4.14 meter. All right. Now what is FS? FR is W10 delta. It is the sliding resistance. Okay. 4.5 plus 8.552 times 17.5 times 9 into 1036. So these are, so before what we did so similarly before we had calculated the weights, right? Now also they are calculating the weights. Now they are taking this triangle, one triangle and one trapezium like this they are taking. Okay, they are taking and they are doing the problem, solving the problem. Okay, that's all. Okay, so what is it? This trapezium, this to calculate the weight, what they are doing, they are taking this trapezium they are taking. Okay, this trapezium they are taking and they are calculating the weight. So, what is the area of the trapezium? Half sum of parallel sides into height. Okay, so half sum of parallel sides, half sum of parallel sides is what? 8.5 plus this much 4.5 here. Oh, okay, times the height 9 meter times the unit weight 17.5. That will give you the weight times 10 delta. There is a friction coefficient between this strip and the bottom original ground, the foundation soil. That will give you the frictional resistance, right? The frictional resistance, that is what they are doing. This is what they're doing. So this one comes out as 744 kilonewton. Okay. Now PA is 184.28 kilonewton. What is PA? PA we already know the uh, uh, disturbing force FD. The disturbing force, it is nothing but my PA is the external earth pressure. So what is my factor of safety in sliding? 744 divided by 184.28 is 4. It is greater than 1.5. So is okay. Now next is my factor of safety against overturning. So what? Resisting by overturning moment. So what is my resisting moment? Again, you find out. So 9 into 17.5 into 40.5 by 2 plus half into, these are the areas, huh? What, how they are calculating? They have to calculate while calculating the moment, what they are doing, they are taking this 4.5 times this rectangle they are taking this rectangle they are taking, and this triangle they are taking. Huh? This triangle they are taking. Right. Okay, that's all. This triangle they are taking. You can do this similar to the previous problem also by dividing it into two big rectangles. That will also you can do. Just the main thing is that the weights and the loads, all everything should be accounted for. The way you solve it, it doesn't matter, but everything should be accounted for. In that book, this is how they have done. So I am also doing that thing. Thing is come out as 3, 4, 3, 2. So what is our resisting moment is PA times H by 3. So the what turning moment? 2, 3. Vector shifting in overturning. 2 by 553. 6.3. So this is fine. All right. Okay. So I hope you understood everything. And in tomorrow's class, what we will be doing, we will be solving one more problem related to this thing, the soil, this designing. And then what we will do, we will go to design of, say, let me see, I will check once. We can do designing or embankments, or we can directly go to as per what codes that I have given to you. As per that only we'll go. So we might do this, or what we might do, we might initially we'll be solving one problem from similar problem, whatever we solved today. And after that, what we will do, we will go to, okay, we will do solve for the embankment. Let us say we can do that. And also with that, we will do the reinforcement for unpaved roads also. We will do, okay, because we don't have much time, na. Today is the fourth class, so last three lectures we have to cover everything. Yeah, we will do this. Okay. So thank you so much for attending. So if you have any doubts, feel free to reach out to me anytime. And yeah, if you have any problem, I'm always available. If any doubts, please feel free to message me, WhatsApp me anytime, email me. And yeah, so please solve whatever, and remember about this problem, please solve this problem as per this design. Okay, yourself, please redo this and check for how what are the differences that you are getting. Okay, so thank you so much for attending the session, and have a great evening. Okay, thank you and see you tomorrow.